So that's great. Cos is what you want to talk about. So the way to do this is I'm going to pull out my regular computer here, and we'll look at a payoff table. So you find, but until I've drawn this on the graph, I think I'm quicker to just like pull it up on a laptop. So the basic idea behind payoff tables is they're just another way to show payoffs to individuals, right? So when we thought about profits, for example, we just mapped profits against output. But the only thing that drove profits for an individual firm is how much that one firm produces. So you could put this in a nice graph. The thing with payoff tables is if how much you make also depends on actions by others, you can't no longer just draw the profit curve for one firm because you've got to figure out in another dimension what's the other firm doing. So a payoff table is just a fancy way of drawing essentially a three-dimensional graph, but just showing it in a table. So it shows me the profits for each firm, profit for firm A, profit for firm B, all in one nice table. So now I just got to quickly find this. Will take me 2 seconds here. IES, PowerPoint, even though it's Keynote. Was it lecture 23? Yeah, on fire. Here we go. And what happened? Nothing. Oh, here we go. So right, well we got. Let's look at Kos again because he's so good looking. He's a nice man. But what you've got here is essentially the profits for each firm, right? So a profit function just told me the payoff for one firm, holding all other firms' activities constant. The payoff now shows me profits for a chemical firm if it produces 0, 1, or 2 units, right? In the old days when we just looked at profit holding everything constant, right? If the rest of the world is held constant at 0 votes right here, then the chemical firm makes $0 in profit for 0 units, 10 for 1 unit, 15 for 2 units. So what this does, it just adds the second firm and adds another dimension. But it's the same thing just shown differently. The thing where it gets confusing is why does this help us figure out what these firms are going to produce, right? So the key assumption here is one of perfect information. This means the chemical firm knows what the boat firm's payoffs are, right? And the boat firm knows what the chemical firm's payoffs are. This in the real world, that's not the case, right? So they might have an idea, but what the exact magnitudes here is they usually don't know. So the way this is set up here, if we were game theorists, there's a dominant strategy here, right? There's a dominant thing for the chemical firm to do. So if we look at the chemical firm's 3 actions, it could produce 0, 1, or 2 units. No matter what the boat company does, if it produces 0 units, it makes $0 in profits, right? If it produces 1 unit, it makes $10 in profits, which is better than the $0 it would make otherwise. If it produces 2 units, it makes $15 in profits. So in each state of the world. So 2 units dominates producing 1 unit or 0 units. So we know that the chemical firm will produce 2 units because it doesn't care what the boat company does. It's best off, its profits are maximized when it produces 2 units. Let's ignore what we know now, and let's see if the boat company has a dominant strategy too, just to reaffirm this way of thinking. So the boat company has $0 in payoffs. So if it rents 1 boat right here, it gets $14 in profits if it's a clean lake, $10 in profits if it's a slightly polluted lake, $2 in profits if it's a really polluted lake, right? If it rents 2 boats, it's better off if the lake is really clean, right? It makes $15 instead of $14. But now it's worse off if the lake is mildly polluted. It would have made $10 if it would have rented 1 instead of 2, and it loses $3 here instead of making 2 here. So this boat company doesn't have a dominant strategy. It's not 0, 1, or 2, right? Its payoffs really depend on what the other firm does. So if you look at solving what actually happens in equilibrium here, you always look at if one of the sides here has an optimal strategy independent of what the other one does. And these are the only examples I would ever give you in an exam. You can go totally insane. In game theory, you can make these tables as complicated as you want, and then there are different types of equilibria, but we're not going to go there. If I make you do something like this, there'll be a dominant. For one of the firms, something will be optimal, like here. So what we now know is, well, the boat company doesn't really have to consider these 2 rows right here because it knows the chemical firm will never be in these 2 rows here. It'll always be down here. So now the boat company knows, since the chemical firm will pay 2 units of pollution, its choice is between $0 in profits, $2 in profits, or $3 in losses. So what will the boat company do? 1 boat rental per day, right? And the equilibrium will be 2 units of pollution. So the equilibrium, if we leave these firms alone, will be $15 in profits for chemistry, $2 in profits for boats, total profits of $17. Then you take a step back, right, over here, and you see if there's a single cell in this table that actually has higher profits for society than the one that these firms, if left alone, would actually end up in, right? So here we have 17, 12, 15, 15, 14, 0, 10, 15, bingo, 20, right? So 20 is better for society than the 17 the firms would end up with, and the way we're going to get there is by assigning property rights, right? So you either, and you just stop me whenever you're happy with the way I'm just keep on going, Max. I'm not going to give you the whole lecture, but I think it would make sense to go through, if you give the property rights to the chemical firm or you give it to the boat company, what happens, because that was a little bit confusing, I think. It's still confusing to me to this day. So what Kos's insight was, if you assign property rights and you make them tradable and everybody has perfect information and there's low transactions costs here, what you could do is you could actually get firms, just by assigning property rights, to choose 1-1 instead of 2-1, right? So you want firms to move from here to there. So what the insight here really was is, well, what if you give the property rights to the chemical firm? That means the lake belongs to the chemical firm. What the boat company could do is it could think about providing a bribe or a payment. Let's not call it a bribe. Let's call it a payment, right? To be free. Sorry, this is the boats. Right, we're with the chemistry firm here. So the chemical firm has the property right to dump in the lake. So what the boat rental firm could do, it could bribe the chemical company to reduce its pollution, right? Could it make itself better off somehow than in the case they ended up? So if we look at our original table again, is this the original one? No. Where are you? That's the right one right here, right? So what the boat company is thinking, yes, I can't stop the chemical firm from producing 2 units of pollution, but what if, I could get up here? My profits would rise from $2 to $10. I would be $8 better off, right? So I would pay anything from $8 downwards per unit of pollution to make, I would pay anything downwards from $8 to the chemical company to be free from pollution. So what you've got here is if this company, for example, chooses to pay the chemical company, let's say $7, right, per unit of pollution reduced, what it would do is it would move to this equilibrium and it would take 7 of its dollars and pay it to the chemical company. So the chemical company would end up with $17. It's better off than at 15, right? And the boat company would end up with 3 instead of $2. And that's exactly what that table not this one, but that one does right here. So this one here takes a $6 payment either way. It doesn't really matter. You could do it for 7 too. So here for each unit of pollution reduction, the both firm pays the chemical firm $6. So what this has in the cell here on the top right, for each unit below 2, for each ton you subtract $6 from the profits shown in the previous table. So the previous table here had a 0, right? And here had a 0 too. Here it had to have had so reduce 1 unit at 10, right? Reduce 2 units 14. So you just reduce that and you assign it to the other company. So this was a 0, so now it's a 12. So if we just look at this table and we try to solve it in the same way we did before, is there a dominant strategy for the chemical firm now? $12 across the board, $16 across the board, $15 across the board. So now, no longer is 2 units of pollution the dominant way of going, it's 1 unit. So now the boat firm knows we're going to be in this row. I'm going to pick the highest payoff I can get out of these 3 choices, and that's -6, 4, -1. I'm going to go with this one, and welfare is maximized. Does that make sense? Right? It's a sort of strange way of thinking about the world, but it's a really convenient way of thinking about the world, because what we're seeing here for the first time is how others' actions actually influence my own payoffs. So the way you think about social welfare here is you just maximize payoffs to all agents in the table, right? So you just sum what's in each of these rows here, and if you add these up, this should add up to the same amount you had before, right? So 15, 15, 12, 17, 20, 14, you can do it. 0, 10, and 15. If you compare this to the prior table and you sum it up, it should give you the exact same numbers, right? But what you've switched here is the within-table split of who gets how much by the boat company paying the chemical company $6 for pollution. You could assign the property right to the boat people, and then the chemical firm would pay the boat people, and you would get something very similar. Did that explain it? All right, excellent. Follow-up questions to this one, otherwise we'll take a new question. You guys look tired. It's almost over, right? Graduation is in 10 days. You can do it. Really? All questions answered? You know how to do, welfare consequences of a subsidy? Yes. Let me see. That's totally all right. You're saving trees. May I put this on the desk there so I can see it? Thank you. So this is the 2008 final. I cannot find the answer key. This looks like, oh yeah. Ooh, you have the scrolling in the weird new Apple way. I can't do that. I'm doing that in the old way. Okay. So the California market supply SB4 of electricity is upward sloping, linear, and goes through the origin. The market demand for electricity is downward sloping and also linear. The market is shown in the picture below. In the graph, show the equilibrium price and quantity in this market. Okay. So this is what most questions start with, is right? You have some sort of basic supply and demand curve. Awesome. Now, I have a piece of chalk. Talk about allocating scarce resources. Quantity, price, supply before, supply, demand, equilibrium quantity. If you can't do that, I'm going to fail you. I don't care if you got 100% on everything so far. You should be able to draw this picture. I won't fail you, but still. Okay. Then somebody drops a wrench into a big piece of machinery which breaks the 3 oldest and therefore most expensive power plants. Supply is now limited. Producers can only produce Q double star units of power, which is less than Q star. Okay? So what happens is machinery breaks and you can't supply anymore. So this is supply after. So the new equilibrium is going to be this price and this quantity. I actually drew you this picture on the actual exam. You just had to figure out where the right price was. Using a table, show the change in producer surplus from this breakdown. Would power producers ever be better off with these broken power plants? If so, explain. Okay, let's do it. Consumer surplus, producer surplus. Yes, I only asked you producer surplus, so you could only do producer surplus, but I'm going to do both because I can. Okay, so the pizza slices, I'm going to use A, B, C, D, E. Consumer surplus before was A, B, D. Producer surplus was C plus E. So welfare is A, B, C, D, E. At Q double star, now this is equilibrium quantity, this here is price, so consumer surplus is A, producer surplus is B and C. So A, B, C. So deadweight loss is D and E. So when I was an undergrad, it was really annoying. I would always label my things so the deadweight loss had 3 triangles. One was labeled D, the other one was W, and the other one was L. So you could, it would add up to DWL. It was great. But I don't expect you to get that fancy. So that's the deadweight loss. This is really simple. What does this look like a lot? I mean, we didn't really draw, just for thinking purposes. This looks a lot like if you drew the marginal revenue curve right through here, right? Then you'd set quantity at Q double star and price that high, right? So it looks really similar to what a monopolist would do. So where I'm going with this question is essentially saying is this firm or the set of firms is artificially restricting output, right? By reducing supply, saying, I'm sorry, it broke, wasn't our fault, and what happens? Price goes up, right? And you get something very similar to what the monopolist would do. So the issue here is one that's well known in industrial economics, something called the capacity withholding problem, where you just withhold capacity. It broke. This happens in refineries. They never break. They just happen to be out at times when prices are high. But if you break equipment at the right times and you get prices really high, if B is bigger than E right here, right, the producers have a huge incentive to withhold capacity to have prices go high and get this big chunk B here in terms of profits or producer surplus instead of the little triangle E here, right? So that's the first part. And then the last part, each unit of electricity produced generates a negative externality. Marginal external cost is constant. Max A was hired to figure out the socially optimal output level and figures out that by coincidence, Q double star is the socially optimal level of pollution. Draw the social marginal cost curve in the before case consistent with Max's result. Is social welfare higher before or after the wrench accident? So what am I saying here? Right, so we've been whining here or Max has been whining about these evil power companies are holding back capacity and they're acting like monopolists. Well, power plants produce all kinds of nasty pollution. So what Max is saying is, well, Q double star is the social optimal output level if you take account of an external cost, marginal external cost that is constant. So constant marginal external cost means the marginal external cost curve is flat. So I just shift my supply curve up parallel, and at the optimum that would mean it would go right through this point right here, right? So this here is marginal external cost. So this here is supply before plus marginal external cost. So this is where people in the exam started scribbling like crazy and putting up tables and so on, but you don't need to do that, right? What do I know if there's a marginal external cost and this here is the social optimum? Am I worse off before than I am now? Yeah, right? If Q double star is the social optimum, then Q star is the output level the firms would choose, if left alone. Q double star is the socially optimal output level. Right? It's private cost plus external costs. And this is the right price and this is the right quantity. So if there is this externality, then Q double star is actually preferred to Q star right here. And by breaking the factories, we got to the social optimum. I am not advocating the breaking of power plants in order to get to the social optimum. It's just the way this problem is phrased, it moves us in the right direction. Yes? Yeah. Yeah. It's not always true, right? It really depends, especially when you have nonlinear curves. It's not clear what's optimal for you to do. So all I wanted you to say there is, and the question is phrased sort of, tell me about, would a firm ever want to do this? And what I wanted you to say is, if B is bigger than E, a firm has an incentive to drop a wrench, right? So just tell me what you're thinking, right? And if what you're thinking is right, you get points for it, and if you don't, you don't. But I'll try and be very precise with the way I ask questions, but I sometimes just want you to look at your picture and tell me what you see, right? And here, the issue was, would a firm do this intentionally? Well, only if it's better off. When would it be better off? If B is bigger than E. Does that make sense? All right, yeah.
So if we had any external costs, but the firms are still facing up to Q star, can you just really explain what deadweight loss would be?
Yes, let's do that. All right, I'm going to make I'm going to draw a different picture because it's going to get super messy. So deadweight loss from an externality is essentially what you're asking. So quantity, price, supply, demand. Okay, I'm going to draw my marginal external cost in here. Firms, if left alone, would produce right here at Q star, P star. But supply just tells you something about the private marginal cost. It doesn't tell you about the social marginal cost. The social marginal cost is supply plus marginal external cost. So social marginal cost, which is private marginal cost plus marginal external cost, is just the sum of these two, right? So you just shift supply up by the amount of the marginal external cost, which looks something like this. So the social optimal point is this one right here. I'm putting price on the x-axis. Come on, Max. So star is usually the optimal one. The only thing that trumps the star is maybe a heart. All right, so this is Q heart, P heart. Right, I'm arguing that this is the social optimum. And what you want me to answer is show me that P heart, Q heart actually has no deadweight loss when Q star, P star does have a deadweight loss. At least that's how I understood your question. Okay, so let's try and show that. So consumer surplus, producer surplus. The key thing here is you need a row for external costs, right? So consumer surplus, producer surplus, external costs, and welfare. Let's do Q heart first, and then Q star. Here the pizza slices are a little bit tricky, right? So I'm going to do a couple, and I'm going to name them in somewhat bizarre ways. So I'm going to come up with a pizza slice A, B, C. Which other ones do I want? I want D, E, F, G, H, J, K, L. Okay, I'm just going to come up with a whole bunch here. I don't need all of these, but they're useful here. Okay, so let's start with Q heart. All right, Q heart, this is price, this is quantity, consumer surplus, area between demand, price, over the range of consumption. It's just going to be A. Private producer surplus, right? So the amount of producer surplus that producers get here is going to be, let's go, B, F, C, E, and D, right? Distance between price and the private cost of production right here. So B, C, D, E, and F. What are the external costs here? Well, the external costs are for each unit produced, I have this much in external costs. I'm producing this many units. So total external costs are the external costs per unit over the range of production. So Q heart, it's going to be D plus K. Now this is where this gets tricky. You could write this down, and then overall finding the deadweight loss gets really tricky. So the better way to do this is to realize the distance between the marginal external cost and the origin right here is exactly equal to the distance between your new and your old supply curve, right? So this distance right here is exactly the same as this distance right here. So the area dk has the exact same area as the area d, e, and f, right? So external costs here, and those are negative things because they're imposed on society, kids getting sick, not going to school, buildings rotting, you not being able to see the other side of the Grand Canyon. So the negative here is minus d, minus e, minus f. So total welfare is going to be, cancel some things out here.